In this video, we'll attempt to evaluate the following improper integral from 1 to infinity of t times e to the minus 2t dt. You might recognize this kind of example as an indefinite integral as a common application of using integration by parts. And in fact, the appropriate choice here is to take u to be t, take dv to be the remaining portion of the integral. When I differentiate u, I'll go and get a derivative of 1, so du is equal to dt. And when I integrate the exponential, I need to divide by minus 2 to account for the chain rule in differentiation. We're now going to apply the integration by parts formula, which I've written here to remind you, uv minus the integral of v du. And let's do it in the case of our corresponding parts that appear in the box. So uv will be t times the exponential with the minus 2, that expression there, and then I have minus the integral of dv of v du, and du is exactly dt. So I'll be integrating the e to the minus 2t over minus 2. Now keep in mind, this was an improper integral from 1 to infinity, and right now I have an indefinite integral. These expressions aren't quite equal to each other until I evaluate, and I will need to put some reminders in there to do this. What I'll need to do is evaluate this expression outside the integral from 1 to infinity, and then this integral here is really an improper integral from 1 to infinity as well. Let's clean up the expression a little bit. Here's the original term outside the integral. And then this is a minus here and a minus there, so it will become a plus 1/2 outside the integral, and then I'm integrating the exponential from 1 to infinity. Rewriting the first term, I'm going to now calculate the antiderivative here. Again, I'm going to integrate the exponential, so I'll end up dividing by e to the minus 2. I'll be dividing just by minus 2 here, and so I'll get another factor of 2 in the denominator. And this whole expression will need to be evaluated from 1 to infinity. Let's simplify the expression. Down in the denominator here, I have 2 times 2, so that'll be 4, and it'll become minus again. And again, we still have to evaluate from 1 to infinity. What it means to evaluate at infinity is what that really means is to take a limit. So I'm going to take b, and I'm going to use that as a placeholder for this number here that's going to go to infinity, and I need to evaluate my antiderivative above between the numbers 1 and b. So we're going to take the limit as b goes to infinity. I need to evaluate the entire expression at b, so everywhere I see a t appear, I'm plugging in the number b. I subtract, and everywhere I see a t appear, I'm plugging in the number 1, and I get the following expression. We need to do some analysis now. As b goes to infinity, we need to consider what happens to this term and to this term as well. The rest of the expression is all constant, which we'll clean up in a minute. The one interesting part that we see here is this e to the minus 2b, and that is a decaying exponential function because of the minus 2, so you'll see it decay down to 0. The other one is a linear factor times an exponential that's decaying as well. Initially it will grow, but then the exponential function will drive it down quicker than that linear factor, and it will go to 0 as well. So both of these terms go to 0, which means when I take b to infinity, I'll just be left with this right-hand term, which when I distribute the sign through and clean up the expression will become plus e to the minus 2. And then got to distribute that sign through, and it'll be e to the minus 2 over 4 as well here. And so I've got 1/2 of them, 1/4 of them. All day I have 3/4 of e to the minus 2. That number tells me the integral converges, and it tells me that the shaded area under the graph from t of the function t equals times e to the minus 2t from 1 to infinity is equal to this value here.